Hi, good morning. In this session, we'll be running through the key findings and learnings from our project Local Area Energy Planning, or as we call it, LAEP Plus. Our service vision for LAEP Plus is a web GIS platform that facilitates collaboration and engagement, allowing users to view and analyze building level data in order to plan and optimize the siting of multiple low carbon technologies at scale. I'm Christopher Jackson from Advanced Infrastructure and Project Lead, and joining me today we have Dan Layton as Technical Lead, Lily Carnes-Taylor as User Research Lead, Alistair Buckley from Sheffield University, Academic and Modelling Lead, and Tim Crook from Regen, User Engagement Lead. I'll now pass you over to Tim, who'll take you through the problem space.
Thanks, Christopher. So our energy system does not have an owner. There isn't one organisation that decides what should connect where and how that system should evolve. It's a partnership of stakeholders that have historically engaged on a needs basis to get things done. As our system decentralises away from large fossil fuel plant and sees greater electrification of heat and transport, the number of stakeholders wanting to know about that network is rapidly increasing, with most of these stakeholders wanting to know similar stuff, like local authorities want to know where they can deploy energy projects, network operators want to know where these projects might be connecting and their impact, and customers want to know what to replace their heating system with, for example. The problem space here is that gathering the data needed to answer these questions is time-consuming, expensive, or not detailed enough to be useful. There is not even a universal system that links address to building to property. There are a huge number of tools and approaches around, but they are all siloed and do not easily fit together to give a joined up picture. So currently, stakeholders have to do the best they can with the available data, resources, funding, and know-how to plan their energy projects, and this repeats a lot of the same work up and down the country. So a local area energy plan is one route to addressing this, but they take a long time, cost a lot of money, and don't have a built-in feedback loop. Next slide, please. So energy data is not just useful to network operators and local authorities. We're seeing lots of activity in this space, not just with LAEPs, but projects like EPIC, the Energy Planning Integrated with Councils project, the publishing of distributed future energy scenarios data, the Local Energy Data Innovation project, as well as industry consensus to improve data visibility. But access to data is only part of the problem. So the problem space here really is twofold. One, that doing useful stuff with the data once you have found it takes time and resource that many stakeholders do not have, or requires a consultant practitioner to do it for them. And two, sharing data directly with other stakeholders is challenging, time-consuming, and localized. Everyone is repeating effort. The service we propose, LAEP Plus, is a web GIS platform that facilitates that cross-sector collaboration and engagement, allowing those users to view and analyze either building level or aggregated data sets. And it's preloaded with common format, clean and granular baseline data, and is countrywide, meaning everyone is on the same hymn sheet and able to collaborate with confidence. So now I'll hand over to Lily to dive more into our user research findings.
Thanks very much, Tim. So in phase one, across the discovery and alpha, we conducted over 50 interviews across organizations and teams involved in local area energy planning and project plans. Despite considerable variation in approach and implementation, some clear trends emerged. At a minimum, both strategic and project level plans tend to require collaboration between the three core user groups you can see here: local authorities, energy networks, and practitioners. We found common challenges and needs emerged in 6 core user personas and a further 8 secondary user personas. It was these personas that guided the user stories that formed our product backlog that built the development prototype tool we're going to show you today. But first, let's look at a user journey. It was user journey mapping that was used to detail the tasks, the data sets, the tools, and the challenges faced by interviewees across their involvement with energy projects. This is a representative one, a project level feasibility study led by Alistair. He's a project manager at a local authority. Alistair's boss, the environmental policy lead, has set net zero targets, and they include a commitment to reduce gas heating. Alistair's job here is to explore the feasibility of deploying low carbon heating technologies within his local authority region. He's got a budget of 20,000, but ideally it's going to cost less, as that's money that eats into what's available for other projects. So there's a lot of different stages and tasks that go on, but here I'm just going to focus in on the challenges, and we can see one emerge straight away at the beginning. Identifying what technologies are suitable where is hard without the baseline data that highlights opportunities. So in this case, Alistair almost immediately had to engage the help of an expensive consultant, but the consultant themselves could only explore a handful of selected regions as they have limited access to data for zoning and optioneering themselves. Months of data, and £10,000 in this case, was spent sourcing and modelling the baseline data needed to build a business case. On top of that, single technology tools made it difficult to plan strategically and consider options like smart local energy systems, where multiple technologies are cited together to improve overall efficiency. And throughout, communication and collaboration was difficult without common datasets and collaborative tools. In this example, it took 6 weeks alone for Alistair to get network capacity data from the distribution network operator to understand the cost and the feasibility of the grid connections at the limited selection of sites the consultant explored. Overall, that meant developing an energy plan was slow, expensive, imprecise, and confusing. We coded and tagged 50 similar interviews with potential users of LAEPapps, which highlighted clusters of common problems and needs shared across groups and personas. Some needs, such as centralized financing for strategic plans, like local area energy plans, we can't address, as these require regulatory change. But we can confirm they do not limit the scope for LAEPapps to deliver value. Many other needs we can address, a sample of which you can see on your screen, such as conducting rapid cost-benefit analyses, creating visualizations suitable for onboarding local residents, and a need for an opportunity finder that assesses the art of the possible. There's a longer list of needs to go through, but today I just want to focus on 3 of the most pressing, and they're around the data and the collaboration. There were 2 key data sets that came up repeatedly and were needed across almost all strategic and project level plans. The first, reliable building level electricity demand profiles. These are useful for local authorities and consultants who want an accurate baseline of existing energy consumption upon which to target the deployment of low carbon energy systems. They're also really valuable to energy networks who need to model demand accurately down to the distribution grid in order to avoid overly conservative and costly investment decisions. Without that data, lower accuracy models or data access requests take weeks and can only be done for a handful of sites. The second dataset, and the single most requested by all the users we interviewed, was low voltage network topology and capacity data. That's needed for planners to identify areas of high capacity and constraint, which may be suitable for different technologies and infrastructure upgrades. That's also needed in order to estimate the cost of grid connections. And without this data readily available, as we saw with Alistair, it takes weeks to request the data from a network operator, or even longer to engage a consultancy to model the network. The final need that we want to focus on today was around collaboration. A WebGIS platform we identified was needed to geospatially view and collaborate on plans in order to cut out weeks of time and confusing back and forth emails between the many stakeholders involved. I'll now pass over to Alistair to talk about the development of those 2 data sets.
Thanks, Lily. So building on Lily's user needs, there are 2 technical goals that we've been working to solve. The first is to generate building-specific electricity demand estimates at half-hourly resolution, and the second is to map the buildings to the low-voltage network. And together these will allow a step change in the way planning decisions for the deployment of low-carbon technologies can be made. So in phase 1, we've built the validation tool for the building-level demand estimates by developing a way to infer the aggregate demand for groups of around 5,000 buildings. So that's for each middle layer super output area of the UK, or MSOA. And we've done this using national electricity settlement data and demographic and building stock statistics available at MSOA. We've also demonstrated the creation of electricity supply regions associated with each MSOA so that current and future electricity demand can be visualized. And we'll show a video of this in a minute or so. Our established MSOA mapping is already more granular than much of the state of the art, which typically concentrates on primary or bulk supply points. We'll build on this work in phase 2 and use half-hourly metering data from tens of thousands of individual buildings to create a much more granular classification scheme that will allow much more accurate estimates of any individual building's demand. And we'll be able to measure the accuracy of these estimates using the inferred MSOA data from phase 1. So I'll pass over to Christopher now for that demo.
Thank you. So we combined these two approaches in a collaboration with Octopus Energy's Centre for Net Zero as part of London Action Climate Week using the LAEP Plus platform. What you can see in this video is the half-hour electricity demand profile at MSOA level for all of London on the coldest day of the year in 2021. You can see in the bottom right graph the MSOA electricity demand peaking at around 6 p.m. as you would expect. In the second video, we projected 10 years into the future to 2031, in which now heat is supplied by up to 400,000 heat pumps distributed through London's MSOAs, shown by the height of the green bars. When we get to that 6 p.m. peak, we see that some MSOAs turn red as they exceed their 2021 capacity. This shows that these areas require a reinforcement strategy such as flexibility or smart tariffs. As our third technical challenge, we've also prototyped a web-based application built on open source GIS framework, DECGL. DECGL is a new GIS framework initiated by data engineers at Uber and designed for visualizing millions of data points and complex networks. We've built a big data streaming engine to progressively stream terabytes of energy system data. Combining these two deliverables and these capabilities allows users to search and filter large data sets across wide geographic areas for zoning, optioneering, and optimization. I'll now hand you over to Lily for a demonstration of the LAEP Plus prototype.
Thank you, Christopher. So, after assessing the problems and needs of users in a discovery phase, we translated user needs into user stories, and they formed a product backlog. At Alpha, we built this prototype tool, which demonstrates the most important features from this backlog. We prioritized the most significant user stories and the most technically challenging. Alpha Research trialed this prototype UI with users and industry bodies to inform feature development and validate the assumption that the tool saves both time and money. We found the tool would halve the cost of flexibility assessments and cut data sourcing time from weeks to minutes, equating to an average saving of 10,000 for a feasibility project, or approximately 25% of the cost of a local area energy plan. What you can see right here is one of the reasons why. It's building stock data, pre-processed, displayed geospatially, with addresses linked to UPRNs and postcodes, all in common formats. We're now going to run through Alistair's user journey again, the project manager at a local authority, and use the LAEP Plus service to see what he can do. Straight away, instead of selecting only a handful of regions for analysis, Alistair scanned his entire region for opportunities, zoning and optioneering. In this case, he's filtering with a traffic light system that represents the available energy network capacity around low voltage substations. Red represents high constraint, where new connections are likely to require substantial upgrade time and cost. Green indicates spare capacity. On top of that, he can then layer valuable socio-demographic datasets, such as fuel poverty or transport networks. In this example, it's EPC rating. The different colored houses represent different EPC brackets. And immediately here, we can see a good region for easy wins. An electricity supply area with high spare capacity and lots of red houses in the D EPC bracket. Here, a combination of home insulation and heat pumps would greatly increase comfort levels and reduce carbon emissions. For the moment, Alistair just logs the opportunity. He wants to focus in on a region at the north end of the map, next to a hospital and some council-owned offices and social housing. He has a look at what he's got. He hovers over buildings to explore the housing stock. He can also select an individual building and view its model demand profile using LAEP+ inferred energy demand profiles. Let's take a look at what that looks like first. If he's interested in a region, he can also select a group of buildings and view the total half-hourly demand for all of them at once. The graph you'll be able to see in a minute shows the minimum and maximum demand for all buildings in the selected area. You can see the expected peak of electricity demand around 6 p.m. here. This type of demand data is hugely valuable for conducting rapid feasibility studies and opportunity finding. What Alistair can also do is run a time series analyzing the modeled demand and linking that to the low voltage network capacity. So what he's bringing up here are the low voltage electricity supply areas, and we'll also show you the substations linked to those. Here they're represented by yellow circles. You can see them expanding out across the city. But zooming back in, we're going to look at a time series and check out in more detail what the capacity of the network looks like. As you can see, now we're looking at it closer, some of these low voltage electricity supply areas are actually close to maximum capacity. You can see them going orange and red in the late afternoon, early evening. That suggests the cost to install heat pumps could be quite large, considering the network's already congested. So at this point, a consultant might instead come in and choose to prioritize a heat network. Using the hospital as a heat source and only minimal additional electricity demand to pump hot water from the heat source around the rest of the heat network. In this case study, the consultants built that network in Thermos. You can see the same buildings here, but there's no baseline data in Thermos. So in seconds, Alistair's able to download that Thermos model and import it on top of the baseline data here. So how does the proposed future scenario look? The platform does that by analyzing the imported model and comparing it to the baseline data. What you'll be able to see in just a moment is that the imported Thermos model doesn't overload the capacity of the electricity network. So that's good news. The next stage that Alistair wanted, if we recall our user journey, was a cost-benefit analysis, giving the cost, carbon emissions, savings, and the financial return of the project. He can bring up those key figures if he wants to just view them simply, or he can also download an Excel with a complete financial model of the project, so he can share that and promote a strategic business case. Finally, Alistair can share this Excel, or he can also share any project in the browser with different stakeholders and customize their access permissions. That means stakeholders like distribution network operators can view the plans for their region and better understand what strategic investments are required. They can also easily visually convey the business case with other stakeholders and get buy-in from key decision makers. I'll now hand over to Christopher to summarize.
Thanks, Lily. So the key takeaways from our session today are: LAEP+ is a web GIS platform that facilitates collaboration and engagement, allowing users to view and analyze building level data in order to plan and optimize the siting of low carbon technologies at scale. LAEP+ offers key pre-processed data sets that make low carbon energy system siting faster and cheaper. And thirdly, the LAEP+ prototype has been validated by our user groups, suggesting the service with half the cost of feasibility assessments and cuts data sourcing time. This equates to an average saving of £10,000 for a feasibility project and 25% of the cost of a local area energy plan. We'll now try and answer your questions the best we can, and I'll hand you back to Fabio.
Thank you, Christopher. Excellent presentation, brilliant demo. Amazing. And yeah, so please, I will invite all the attendees to to ask their questions in the chat. We have a first question from Jonathan. It is, do you look at gas demand as well as electricity demand at the building level? Options to transition heat from gas to electricity will need an understanding of the heat-driven energy demand.
Okay, I'll have a go at answering that. So the analysis we did with the Centre of Net Zero did exactly that, where they used their data set of around 500 gas customers with smart meters to understand exactly what the heat demand timings were. So we acknowledge doing the same analysis that we're performing with electricity demand needs to be replicated in the gas space. And we think that our methodology is able to essentially be transferred straight across. So while that's not within the scope of our beta project because of cost and resource limitations, technically we're comfortable that it's entirely feasible. It's also important to bring out the point of interoperability, and I know yesterday City Science and Lee spoke of this, and we've talked at length about it, that the underlying ontology is connecting those building stock models between the gas and the electricity profiles also need to be aligned and interoperable. And as he mentioned, we would be happy to work together to ensure that that's the case.
Thank you, Christopher. And yeah, I'm wondering if you have a plan on how to do this with City Science, or you're just starting this conversation?
It was raised a few weeks ago. A definitive plan is difficult in the first phase of this project, as I'm sure that you'll know. But the understanding the use cases and the requirements for the ontologies to match over was a really important step.
Okay. Thank you. And actually, I have a question on the user stories. So Lily have briefly mentioned that you identified some priorities, some user stories that need to be prioritized. Can you give us some details on which are those that you have decided to prioritize?
Yeah, sure. So the big one that came up most often for example, the local authorities, there were two key user personas there. One was the local area energy planning lead, typically also the environmental policy lead. And then below him is a whole load of project managers. And one of the main user stories that came up repeatedly for those was a difficulty understanding and communicating with distribution network operators, who often use a very, very different language, very different set of terminologies, and have their own processes for how connection requests and information requests turn about. But that's enormously hard for a project manager or a local authority employee to get their head around. So that was one of the first things we prioritized doing, trying to get everything in a common format that's visual, so that the DNO can keep their processes and see the complexity that they need, but a local authority can just see the key metrics and a nice visual.
Very nice, very nice. Thank you, Lily. We have some questions in the chat. The first one is, we'll modify this a little bit, seeing what are the commercial opportunities that you have identified for this platform?
So I'm happy to take that one. So for each of the user groups identified, we have beta customers who want to trial this service in phase 2. We can speak at more length later on in the day, but we've identified sort of the core value propositions, the money saved or the additional service performed by LAEPapps, which would lead to clear commercial revenues. And we've benchmarked the cost of the service against similar products in the industry, both subscription-based and data-based, and see that there's a clear commercial model for the software for all three user groups.
Thank you, Christopher. And maybe may I ask what will be your preferred model in this case?
Yeah, sure. So the cost, the preferred model would be a subscription model based on £10,000 per user, and this has been come to by looking at essentially range in the marketplace between about 1,000 to 30,000, depending upon the capabilities of the software. So we feel comfortable that 10,000 per user is reasonable. On a data-only model, we're pricing the service at 15 pence per building, which again is very competitive compared to other proprietary data sets used in the insurance sector, for example, which is around 5 to 20 pence. And also, indeed, the Energy Systems Catapult's own local energy area representation, which comes out about 25 pence per building.
Thank you, Christopher. Thank you very much. And we have a question from Jonathan that is, what data challenges do you see for scaling this solution, for scaling up this solution? For instance, missing data. An example is the low voltage network topology or the data around the capacity. This type of data will clearly be an issue, as well as commercial barriers.
If Dan wants to come in on technical scale, because that's worth picking up, but I'll just quickly, first of all, cover off the questions of missing data sets. Yeah, sure. So there's a big problem of uncertainty in the data available in the energy system, and a real challenge is distribution network operators specifically are very uncomfortable with uncertainty and missing data, and they don't want to put data in the public domain in which they don't have full confidence of. On the other end of the scale, the actual end users and project developers are very comfortable with uncertainty, and there's much more uncertainty in the business model and the commercial uptake of the projects that we're developing. So relatively, the uncertainty in the missing data in the energy system is less significant than the uncertainty in the commercial risks of most low carbon technologies. So essentially what we do is, as we piece together missing data sets, we record and measure the uncertainty that they have, so that can be incorporated in the decision making of the end user.
I mean, just in terms of
coming on scale.
Yes, I was just going to say, just in terms of scale, I mean, the reality is that there is missing data. Our key thing, therefore, is to make sure that when the data becomes available, it can be ingested extremely quickly, and it can be queried and searched and stored extremely quickly, a great deal quicker than it currently can. We've built the prototype using a big data approach rather than a classic SQL database approach, because we found very quickly that the data was at too large a scale to just stick it in a database. So we built this microservices platform architecture using big data tools, and it means that and there's a whole series of connectors and translators and semantic brokers which allow data to be ingested from wherever it comes. You know, the classic thing is turning XY data into log. We built a tool to do that automatically. So this really helps with scale, and it's all about getting the platform right at the beginning and building it from day one on a modern data platform that can handle that scale of data.
Great, thank you, Dan. Thank you, Christopher, as well. And we have another question from Steve that is, well, basically connected to some of the points you touched before. That is, how do you see LAEPapps working alongside the ENA's National Energy Systems Map?
So that's a really interesting question. We spoke at length with Matt Webb, with Gabriel Barnard from SSGN, Matt Webb from UKPN, who are all leading the work at the ENA's digital system map. They still haven't defined exactly what the outputs are, but their clear view was that the service should support innovators and not intend to replace them. So we see that there's ample opportunity for us to take the outputs of the digital system map and incorporate them in a better and more detailed digital twin upon which our end users are building their low carbon systems. So we indeed wish that the digital map was already available, so it could be incorporated into us, and we will be joining the stakeholder group as soon as that becomes live in the coming months.
Thank you, Christopher, and well, thank you to the team Thank you, Lily. Thank you, Dan. Thank you, Alistair. And yeah, we are now reaching the next step of this event. We have a break now. The Advanced Infrastructure LAEP Plus team will be on the call. So please, if you have other questions for them, write them in the chat. I'm sure they would be more than happy to answer. And see you at 11:30.